In this video, I'm going to talk about the concept of differentiability, and the idea of differentiability is whether or not a function has a derivative at a particular value on a curve. And this ties in or connects to another concept called local linearity. So, in order for a function to have a derivative at a point c f of c, the function must be locally linear at x equal to c. If the function is not locally linear at x equal to c, then the derivative at c is not defined. In other words, the function is not differentiable at that point. Alright, so let's talk about this concept of local linearity before we get any further into the idea of differentiability. So we've talked about the derivative being instantaneous rate of change at a point on a curve, or the slope of the tangent line. So consider a simple curve, y equal to x cubed. This is not the best graph, but it gives you a pretty good idea. Y equal to x cubed. If you were to if you were in an airplane, and let's say that this function, y equal to x cubed, is the road in your neighborhood. So the road in your neighborhood looks like y equal to x cubed. If you're flying high above and you look down over your neighborhood, you would actually see a curve. You would see the curve y equal to x cubed. Let's assume that your house is right here at this point on y equal to x cubed, and we're going to call that c f of c. If you were to get closer and lower your altitude in the airplane, instead of seeing this global curve of y equal to x cubed, you would start to see less and less and less of the curve. So basically the curve would start disappearing as you zoom in or get closer to your little local part of the neighborhood. And the closer you get, the less that this curve would look like a curve, and it would look locally linear. And that's that whole idea of local linearity. And it kind of makes sense if you think about it. When we think about slope, we think about lines having slope. So that's why when we zoom in and zoom in and zoom in on a curve, if there is a derivative, we will get this idea, or get this concept of local linearity. So there's a connection between local linearity and differentiability. Alright, let's take a look at let's get this out of the way. Let's take a look at three particular functions to try to get this concept. So I'm going to bring up my calculator here, and I already have the functions typed into the calculator. I have y equal to x squared, y equal to the absolute value of x minus 4, and y equal to x plus 1 to the 2/3 power. So let's start by looking at y equal to x squared. So I'm going to bring that up on my calculator, and you will notice that I've turned the axes off. I want to investigate the vertex of this parabola. And the parabola looks something like this, and it opens up. And I want to determine whether or not the function is locally linear at x equal to 0. Or I'm really trying to figure out whether the function is differentiable, has a derivative, or has a slope at x equal to 0. So if I use the zoom in feature of my calculator, and that would be zoom 2 if you're using a TI, and I press enter, well, the curve is still curvy, but it's less curvy than it was. So I'm going to zoom in again, because remember, we're trying to get a local view. We're still fairly global right now. And enter. Okay, it's not happy. Let's go back. Zoom. I can quit. Alright, zoom 2. Alright, do it again. And let's do it two or three more times. And you can see that at x equal to 0, the curve is getting linear. And in fact, if I zoom in one more time, it will appear that I have a horizontal line at x equal to 0, and that is the slope of a horizontal line is 0, and that is the derivative of this function at 0. So this function, yes, is differentiable at x equal to 0. Now if you take a look at the window, if you want to know how close I am, remember we were zooming in on 0, And if you look at the x minimum and the x maximum, we are very zoomed in. And you look at the y minimum and the y maximum. So in this case, the line that's tangent to the curve, well, a little bit of a miss there, but you get the idea. So the tangent line at x equal to 0 would be horizontal, so the derivative at x equal to 0 would be 0. And our big idea here is that, yes, the curve's locally linear and differentiable at x equal to 0. All right, let's take a look at our next function. I'm going to go back to y equal to, and I'm going to turn off x squared, and I'm going to turn on the absolute value function, and I'm going to go back to a zoom 6 window. Now, if we go to x equal to 0, so I'm going to do zoom 2, and I'm going to move to the curve at x equal to 0. Not going to be exact, I'm just going to get as close as I can. We should be getting an output of 4, so that's pretty close. I think if you'll see, I'll maybe zoom in one time, but the x equal to 0 is already on a linear piece of a piecewise function. Remember, an absolute value function is made up of pieces of two lines. So x equal to 0 is right over here. So if we zoom in on that, we're obviously going to get local linearity because it's basically sitting on a line already. So at x equal to 0, the function is locally linear. However, let's take a look now at the vertex of this absolute value, which would be x equal to 4, and let's zoom in and see what happens there. So let's go back to a standard viewing window, and let's go to zoom, and let's move the cursor over to the vertex as close as we can get it. Maybe a little. So either one of those I think would work, and press enter. Okay, doesn't look like we had much of a change there, so let's do it again. Get as close to 4 as I can. And doesn't look like a whole lot of change there. So I'm going to zoom in again. Move the cursor as close to 4 as possible. Looks like no change. I think you're probably beginning to get the idea. Zoom 2. Enter. Let's see how close we are to the x value of 4 by looking at the window. We're at 3.960 and x maximum 4.038. We're pretty close to 4. And you can, if you want to spend a lot of time zooming in, you can continue zooming in, but we're not going to get local linearity, so there's no local linearity and not differentiable at the vertex. Now bear in mind that in number 1, on the parabola, the function was or is differentiable at x or at the vertex, and in the absolute value function, not differentiable. So in a moment we'll talk about, well, what's the difference and what are the similarities. All right, let's go to the third function, and let's turn off the absolute value and turn on the last function and go back to a standard viewing window of zoom 6. And eventually the calculator hopefully will give us a graph. Let's go back. Maybe, oh, you know what? I didn't turn the function on. That's what's going on. All right, turn it on. Zoom 6. Let's try it now. All right, so we get a function. I call this the bird function because it kind of looks like a bird flapping its wings. So the function looks something like that. And the vertex, or so to speak, of this function is at x equal to -1. Therefore, x equal to 0 would be to the right of that, somewhere over here. All right, so I'm going to start by zooming in on x equal to 0 because we want to investigate each curve at x equal to 0. Zoom 2. Move the cursor, or move it up to the curve as close as possible. We should be at about a y value of 1. Okay, so that's pretty good. And then let's zoom in again. And move to, so we're we're good there. Maybe move it up a little bit. Yep, that's good. And it looks pretty linear. I'll do it one more time just to see. Zoom 2. Move it down a little bit. We're almost at 1. That's pretty good. And we can keep zooming in, but we're pretty much getting a line on our screen. And if we look at the window, we're very, very, very close to x equal to 0. So at x equal to 0, we do have local linearity, and there is a derivative there, so the function is differentiable at x equal to 0. Now let's go back to the standard viewing window and take a look at what's happening at x equal to -1. Okay, so I'm going to zoom in, and I'm going to move the cursor this time to -1. That's pretty close, and press enter. I'm going to do the same thing again. Get as close to -1, 0 as possible. And if you think of this as a bird, kind of like I mentioned before, it looks like the bird is starting to raise his wings, so to speak. -1, that's pretty good. Maybe a little more to that way. Enter. And maybe a couple more times, zoom to whoa, that's pretty close right there, 0. And what's happening is it kind of looks like, and if we did this over and over and over again, I don't want to, in the interest of time on the video, I don't want to overkill here. It looks like, as I said, if this was a bird, the bird is raising its wings, and eventually, if we keep zooming in, what we would see is a vertical line. Now let's think back to Algebra 1. A vertical line has slope that's undefined or no slope. So if the slope is undefined or no slope, if there's no slope, there's no derivative. So the function is not differentiable. So you might say, well, isn't this vertical line, isn't that locally linear? Yeah, it is, but a vertical line has no slope, it's undefined, so the function is not differentiable at that particular vertex. Alright, so we'll put a little frowny face there. So what's really going on here then? Why is the parabola, why does the derivative exist at the vertex but not on the other two? Well, let's take a look at the formal definition of differentiability. A function is differentiable at a particular value of x, called c, if the limit as x approaches c from the left of the slope function, because remember that's the definition of derivative, that's the slope, is equal to the limit as x approaches c from the right. In other words, the derivative from the left and the derivative from the right must agree with each other. So the left-hand derivative and the right-hand derivative must agree with one another. Well, what does that mean? Well, let's go back to the curves. If you take a look at the first function, y equal to x squared, and let me erase that tangent line that I have there. And let's think of a series of tangent lines. I want to get rid of some of this stuff, but I don't want to get rid of my curve. If I were to take and draw the tangent lines at various points, let's go to a blue here, here, and here, and here, and here, and here. What you would notice, so here's the tangent line here, the tangent line here, the tangent line here, the tangent line here. As I continue to draw these tangent lines, what's happening on the left-hand side is that those tangent lines are basically moving me towards a tangent of x equal to 0. And eventually I will get that horizontal tangent. On the other side, the same thing is happening. If I draw the line tangent at this point, and draw the line tangent at this point, and draw the line tangent at this point, and draw the line tangent. So this is kind of what we're talking about with the left and right derivatives agreeing with one another. The slopes as you come in from the left are agreeing with the slopes as you come in from the right, and they're both guiding me towards a slope of 0 at the vertex. Now, on the other hand, if we look at our next function, which was the absolute value function, and we look at the vertex. Let me erase some of this stuff and get it out of the way. Erase some of this. Bear with me a second. Now, if we look at the vertex this time, notice that we have two line segments coming together. So the slope of this entire line segment everywhere except at x equal to 0 is a slope of 1. And on the other side, the slope at every value of x except 0 is positive 1. And I think I said positive 1 for the other one when it really should be negative 1, so make that correction. So notice that these two slopes are not agreeing, and they're not slowly or gently guiding me to a horizontal tangent or any kind of tangent line at the vertex of x equal to 4. So that the derivative on the left-hand side, or from the left, is not agreeing with the derivative on the right-hand side. And then in the third scenario, we already talked about the fact that when we zoomed in, we ended up getting what was looking like a vertical line, and the slope of a vertical line is undefined, and there's or no slope, so it's not differentiable there. So in this case, the curve is guiding me. If I draw in the tangent lines, I will get, this board's kind of hard to draw tangent lines and hit the point. What's happening is the tangent lines are getting steeper and steeper and steeper. Same thing on this side, they're guiding me. But what they're guiding me to, as I get closer to that vertex, is they're guiding me to a vertical line. So that kind of gives you a graphic representation of what's going on. So the implications are a function is not differentiable at a sharp turn. So if we highlight that, so the sharp turn case would be what we had in our absolute value. Oh, well, let's grab a pen here. That would be our absolute value. There's a sharp turn at the vertex. A function is not differentiable at a cusp. A cusp is kind of like a dimple, and that would be kind of like the bird function. We have a cusp here. The function is not differentiable at the cusp. And it's probably obvious to you that a function is not differentiable at a discontinuity. So if we have a vertical asymptote, well, clearly there's no y value there. So if there's no y value, there can't be a slope there or at any other kind of discontinuity. So hopefully in this video you've kind of had this idea of that on a part of a curve, a function can have a derivative, but at some values of x there may not be a derivative.